Hello everyone. In this video lecture we are going to talk about hydrogen atom and its spectrum using quantum mechanics. The atomic model proposed by Niels Bohr was able to describe hydrogen atom with a high precision, but more detailed information we obtained from the study of hydrogen atom using Schrödinger theory of quantum mechanics. Here if we ask why do we need quantum mechanics, then the answer is that Bohr's model works well for simple atoms like hydrogen but fails to study more complex systems. And surprisingly, the study of this one electron hydrogen atom is of historical importance because this is the first model Schrödinger studied with his theory of quantum mechanics and succeed in predicting energy eigenvalues, spectrum of hydrogen atom and the detailed behavior of the atom. So we will see how quantum mechanics applies to the hydrogen atom. Quantum mechanical study of any system is governed by the Schrödinger equation, which describes the motion of a particle with mass m in a potential v. So here in this equation the first term is associated with the kinetic energy of the system or the particle, and this second term is the potential energy of the system, and on the right hand side E denotes the total energy of the system. So this is this equation describes the motion of a single particle, but we know in hydrogen atom the hydrogen atom is not a single body problem. It's a two body problem where the electron that rotates around the nucleus on a circular orbit, and also electron that rotates around the around its own axis, and this electron and the proton they interact by a central force which is of electrical in nature and is a conservative field that we already know. So the model we are going to consider here where the hydrogen atom is treated as free atom, so the total angular momentum would be conserved, and also we will ignore the electron spin in this particular model. So this is the equation which describes the hydrogen atom, where r1 and r2 are the position coordinates of the particles m1 and m2. So this m1 is the mass of the proton and m2 is the mass of the electron, and they are in r distance apart. So I mean, though it's a two body problem where nucleus itself rotates around the center of the mass, but the nucleus is so massive compared to the electron mass that the nucleus is considered to be at the center of the mass, and with that consideration the two body problem can be approximated to a single body problem with the reduced mass and relative coordinates. So r is the relative coordinate, which is the difference between r1 and r2, and rm is the position coordinate of the system. So in terms of this new with this new terms, the Schrödinger equation can be written in this following manner. So the first term that describes the motion of a particle with reduced mass mu moving in a central field Vr, and second term describes the motion of a free particle with mass m, where m is the composite mass, that's m1 plus m2. So here in this diagram you can see that the two body problem can be transformed to a problem where the nucleus is completely stationary and the electron that rotates around the nucleus with the reduced mass mu. So now it's possible to split the total wave function, which is psi is a function of r and rm, into the product of two wave functions. One is small psi, that's the function of r, and that describes the wave function of the electron, and xi, that's the wave function of nucleus, that is the proton, which is a function of rm. And this splitting is possible because the center of mass is completely independent respect to the reduced mass. Therefore the single body problem can be described by the following equation, and we are interested in electron motion. So the where the psi denotes the wave function of the electron, and mod of psi square would be the probability to find the electron in space. Now our job is to find the solution of this equation, and we know this that this equation is in Cartesian coordinate, and it's difficult to find the solution of such equation in coordinate space. So our job would be to make our life simpler, and we know that in the problem there is a spherical symmetry as the electron that is rotating around the nucleus, and that symmetry can be explored in finding the solution, and that can be achieved if we transform the Cartesian coordinate into the spherical coordinate system. Therefore the Schrödinger equation can be written in spherical polar coordinate system in this following manner, and we'll expect the solution of this equation as the following. Here we see three new terms, n, l and ml, but where do we get all these? What is the significance? That we'll know gradually. So in spherical polar coordinate system, r, theta, phi are the independent variables. Therefore the wave function psi, that's the function of r, theta and phi, can be factorized as the following, which is r, capital R, function of r, and capital theta, which is function of small theta, and capital phi, that's the function of phi. So with this we can split the single single differential equation, that is the Schrödinger equation, in these three equations. So this first equation is the radial equation, the second, the rest two are the azimuthal equations, and we see the two different constant terms here. One is L into L plus 1, another one is ml square. So these are the separation constants and are required to split the equations in three separate differential equations, each depending on one coordinate, and we choose the constant in this particular form for mathematical convenience. And well, we could have considered L instead of L into L plus 1, but to have proper 2 pi periodicity in the solution, we choose such forms of the constants. Now we write the radial equation again. Here V prime r is the effective potential, which holds two terms. One is 1 by r and other one is 1 by r square with a negative sign. So this 1 by r is the term is the Coulomb potential, and 1 by r square is the angular potential, and is considered to be associated with the centrifugal force, which pulls a particle, that is the electron, outward in opposite to the Coulomb force, and that you can see because there is the negative term in 1 by r square. Now we'll proceed with this equation where mu is the reduced mass of the equation. Now we'll be curious to know how much the mass has been reduced than the original mass. So in the reduced mass formula, if we substitute the proton mass m1, which is of the order 10 to the power minus 27 kg, and the electron mass, which is of the order 10 to the power minus 31 kg, then we get the reduced mass, which is 9.1044 into 10 to the power minus 31 kg, and this reduced mass is slightly smaller than the electron mass. There is therefore no loss in generality. Now let us define some constants so as to make the Schrödinger equation, that is a radial equation, compact. So these are alpha and lambda, and the new variable which is rho, and that is alpha times r. So with all this, the equation, radial equation, looks like this. Now the great job is to find the solution of this equation. How do you do that? In general, we always try to find the behavior of any wave function in rho tends to infinity as well as rho tends to 0 limits. So let us do that. If we take the limit rho tends to infinity, then this equation shrinks to this equation, which is d2 rho d2 r d rho square minus r by 4 equals to 0, and the asymptotic solution of this equation would be r of rho, which is e to the power plus minus rho by 2. But as the wave function has to be finite for rho tends to infinity, therefore the accepted solution is this, which is e to the power rho minus 2, and this solution is for the limit rho tends to infinity. But for any rho, the general solution would be in this form, which is f of rho into e to the power minus rho by 2, where the f of rho is any can be taken as any finite polynomial of the form which is rho to the power s into L of rho, where s is the positive integer, that is it is greater than equals to 0, and this L of rho is the series as the following, which is a0 plus a1 into rho plus a2 into rho square and so on, with the condition a0 not equals to 0, and here ai's are the coefficients of the series. Now if we substitute the function r of rho, which is f of rho into e to the power minus rho by 2 in the model equation, that is the radial equation, we are going to get this in terms of the series function, which is L of rho. And now we can check the behavior of this r in the other limit 2, which is rho tends to 0, and the equation turns out to be this, which is s into s plus 1 minus L into L plus 1 equals to 0. And now if we solve this equation in the limit rho tends to 0, we are going to get these two solutions, which are L into L and minus L plus 1. So now we are convinced for choosing the special form of the constant term, which was L into L plus 1. Okay, so before we write the solution of the solution of r of rho, we have to remember that f of rho should be finite for rho tends to 0 limit. Therefore the possible solution for s is L, and therefore we can write f of rho as rho to the power L into L of rho. Now again, if we put the function f of rho in this equation, then we are going to get this form of equation, and from here we can find the recursion relation for the coefficients. So here we see that a nu plus 1 can be is related to a nu in this manner, where nu is a positive integer and are like 0, 1, 2, 3 and so on. Now if we do the convergence test in large limit of nu, then we see that as we go to the higher terms in the series, the coefficients satisfy the converging nature. So we can say that we are safe here, but the problem arises when this rho is large, that is when rho tends to infinity, we encounter a term 0 multiplied by infinity. So then what would be the way out to find a finite wave function or the vanishing wave function at large limit of rho? So the series has to be stopped somewhere by choosing lambda equals to k plus L plus 1, which can be named n and can be called the total quantum number, because n involves the radial quantum number, which is k, as well as the angular quantum number, which is L. Here the values of total quantum number are 1, 2, 3 and so on, and the angular quantum number or the orbital quantum number runs from 0 to n minus 1, and the another quantum number which is ml and is the magnetic quantum number runs from minus L to plus L. So this magnetic quantum number is related to the effects produced by the magnetic field due to electron motion around the nucleus. Now let us recall the constant terms, which are alpha and lambda, where lambda is related to the principal quantum number n. If we put the upper bound in order to keep the solution finite at a large distance, and are related to the eigenvalue E, and therefore we can write E as the following, which is where E is a function of n, so we put the subscript n, and this negative sign is to denote the bound state of the hydrogen atom, because we choose such a potential that when electron is far from the nucleus, energy is 0, and as we come closer, the energy becomes negative. And here ER is the Rydberg constant, and is a popular limit of energy in the atomic physics, and this ER is mu into e to the power 4 by 2 h cross square. So the remarkable fact is that this energy series is same as the energy bound state series found by Niels Bohr in his atomic model. So here in this diagram you can see the discrete energy levels, and this VR, which is shown by the red line, is the potential and denotes one of the end of the classically allowed region, and the other side of the potential well is on the other side, which is on the negative side, which is not shown here in the picture. So here you see that as n increases, that is 1, 2, 3, 4 and so on, the energy levels they become closely spaced. So what we expect or what we could get from the quantum mechanics, what are the extra features we get from the quantum mechanics, is that in Bohr's model, n defines the angular quantum number, whereas in quantum mechanics n is the principal quantum number, and n is related to the n is the total quantum number and is related to the radial quantum number k, as well as the orbital quantum number L. So now we can have a better picture in terms of this, because we have the other parameters, which is the radial quantum number as well as the orbital quantum number. And so now we can say that if n equals to 1, then that denotes the ground state with energy minus ER and with 0 angular momentum. Although En depends on one quantum number n, but the eigenfunctions that depend on the quantum numbers. As we know, the possible solution would be of this form, which is psi of n, L and ml. So there could be different possible eigenstates with same energy eigenvalue. Let us see how. So suppose n equals to 1, and we know that L is less than equals to n minus 1, therefore the possible value of n would be 0, and then ml would be 0. And then if we have n equals to 2, then we have the like possible values of L which are 0 and 1, and for 0 we have ml value which is 0, but for L equals to 1, ml would be minus 1, 0 and 1. So therefore for n equals to 2 we will have 4 total eigenstates. So for n equals to 1 we see that the number of state is 1. For n equals to 2 the number of degenerate states are 4. So it's 1, 2, 3 and 4, and for n equals for nth level the number of degenerate states are n square. Therefore we see that the Bohr's theory cannot give the concept of degeneracy which we get from the Schrödinger picture. So the solution of the radial equation with upper limit k is r of rho, which is e to the power minus rho by 2 rho to the power l into l of rho, and the radial solutions for n equals to 1 and n equals to 2 are the following. And here r0 is the Bohr's radius, which is h cross square by m e square, and this is the plot for the radial wave functions with r by r0, and these are the radial wave functions for n equals to 1 and n equals to 2. Okay, so that's all. Thank you.